Hi, in this video we're going to talk about multi-level calculations in which one region of the molecule is treated at a higher level of theory and another region, for example the solvent, is treated at a lower level of theory. So in this setup we're going to make a relaxed surface scan of the attack by isopropylamine to a carbon of a acetic anhydride molecule. So the two molecules with the bigger atoms are treated at the DFT level of theory, and the solvent, which is dimethylformamide, is treated at the XTB, extended tight binding model of theory, which is a semi-empirical method, which is quite fast. So first we're going to see the approach of the amine. We can see here that the amine is approaching, then it is accommodating, the solvent is changing its orientation, and then eventually a bond will form. We see here that at some point when the carbon-nitrogen bond was formed, the other acetate group left the molecule. So this is probably a two-step reaction. Then on a second step, the nitrogen would deprotonate, forming an amide bond. Now we are going to take a look at the Orca manual on how this can be done. In here we can see that in this section 8.13.1.7, this may change depending on the Orca manual version. This is 500. So we can choose, in order to do QMMM, this is actually a QM calculation, but we need to put this keyword QMMM on the keyword list, and then we can add a module that is QMMM module, where we can define QM atoms. So there are different onion methods. These are, for example, keywords that are already set up for specific calculations. Usually the second keyword is for a fast method. So XTB is actually XTB2, is the newer version of the XTB method by Grimme. Then we have the old version XTB1, and we have other fast methods like Hartefock 3 corrections, PVEH 3 corrections, R2 scan 3 corrections, and PM3 AM1, etc. XTB, it's more accurate than PM3 or AM1, and it is much faster than HF3C, PVE, H3C, etc. So a 3-level calculation can also be done with QM, XTB, and some molecular mechanics method, but we are not going to see that in this video. So there are many more options that you can check out. I'm not going to discuss all of them, but I'm going to show you now my input file. So here you can see that I'm putting the keyword QM/XTB. And then for the QM method, I am using the PV0 functional with def2 SVP basis sets on all atoms. These are only the atoms from the acetic anhydride and the isopropylamine molecules. So then I choose other standard options. And then this is important. I am defining that the QM atoms go from 0 to 25. So basically, if I go back to Chemcraft, in the coordinates, I have many atoms, but basically only the first 26 atoms from these two molecules are only treated at the PV0 level of theory. So this is important to be sure of which atoms are going to be in the high level space and which atoms, the rest of them, are going to be in the lower level space. So I am using 16 cores and I'm using a memory per core of 4 gigabytes. So I'm specifying this because the shell file that I'm using to run the calculations need to have some information in order for the XTB program to run. So Orca doesn't have an embedded XTB method yet, so it calls an outside program, which is the XTB program by Grimme and collaborators, which is installed on a different folder. So I'm not going to discuss how to install it in this video, but I'm going to show at the end of the video where you can get the program and you can follow the instructions there. But in the shell file, which is this one, a lot of this stuff is standard that I use for running calculations in the cluster, like loading the dynamic library path. This doesn't matter, but these three are specific options that you need to specify in order to use the XTB program with Orca. So I don't know if these options need to be defined each time I run a script. They probably need to be defined only once, but I am not sure how to do that because I'm not an expert Linux user. So these are environment variables that are needed to run XTB. So these are 4 gigabytes probably for the memory that's used per core. And this is the number of threads. So 16 threads, and this is probably in one node or something. I don't know the details again. So then I just run my normal script. And the other important thing is that I'm doing a geometry scan. So you need to do this with Orca version 5.0.2 or later. This is the latest version because there was a small bug in the program in version 5.00. So because this is a QM calculation, not a QMMM calculation, we don't need a force field. But in the previous versions of Orca, it was requiring a force field file, even though it was not really necessary. Sorry, it was requiring a PDB file, although there was no PDB file present. So basically, this is the part for the QMMM method, which is actually QMQM, and this is the part from the geometry scan. So I'm scanning the bond between one of the carbons and the nitrogen from 4.8 to 1.1 angstrom in 38 steps. And this is the rest of the normal input. And if we go to the output, so this is Orca 5.0.2, there's a lot of information, and we can see that there's a lot of setup for QMMM region, active region, a lot of information regarding the method, coupling scheme, subtractive, embedding scheme, electrostatic. I'm not going to analyze all this because I'm just starting to use the QM methods and I'm very far from an expert in this. I'm just showing how you can run a calculation and start working in this method. So this is the relaxed surface scan step 1. There's a lot more information, and I'm going to skip a little ahead because this is a QM calculation. You will get a XTB2 calculation on the full system, so all the atoms, and these are the coordinates of all the atoms, Cartesian coordinates, etc. And then you get the final single point energy of everything. So this is L for low level, and the energy is low because extended tight binding uses effective core potentials for the inner core electrons. So all the core electrons, which are the ones that contribute most to the electronic energy, actually to the single point energy too, they are not accounted for. So always the energies you get with XTB are lower, but of course you can compare relative energies between two molecules or two processes, two parts of a process. So then you do a calculation at the XTB model of the small system, the first 26 atoms, and then you do a QM calculation on the small system. So you get, L was not for low level, L was for large, S is for a small system. So this is the energy of the first 26 atoms, the acetic anhydride and the isopropyl amine at the XTB2 level of theory, and then comes the QM calculation in the small system, which takes much longer. So this is the one that calls the Shark integral routine and uses all the DFT settings. So this takes much longer, but okay, it converts quite fast because it was an organic molecule. And here is the final single point energy, which you can see it is much larger for the small system. So then there's a mixture or an addition of the energies. So basically what you would get is the low level energy of the whole system minus the low level energy of the small system plus the high level energy of the small system, and you get this number. So you will get different information. Then you calculate gradients, etc., and you continue the geometry optimization. This is a very large file, so I'm not going to skip through it, but this is the rest is like a normal relaxed surface scan. And here is, for example, the list of the relaxed scan actual energy, where the energy, the full energy of the QM plus QM2 system is plot against the carbon-nitrogen distance, which I have been scanning. So in order to plot this, I'm going to copy this into Octave. So I'm here in Octave, and I have a small script for plotting. So here I call this data for the information, the distances, and the energies in Hartree. And then I just plot them using a conversion to kilocal per mole. So if I run this, I get this figure. So basically what happened is that the optimal carbon-nitrogen distance was probably around 1.6 angstrom, and then I kept decreasing the distance, forcing it to get closer, and that increased the energy. So this is only a relaxed surface scan. It is useful for seeing what the initial possible transition state and possible product states are. So basically now I should do a second step of the relaxed scan, starting from here, from this distance, and maybe I should scan for the oxygen of the acetic fragment leaving the carbon. This is probably a multi-step reaction because I have NH2 attacking, so I need to also deprotonate. So on future videos I'm going to do this more in detail, but this video was just to show how you can do a relaxed surface scan with QM methods. The XTB method is really fast, so unless you want to study proteins, which are much larger, if you only want to study reactions in a solvent, this is a good method to use because it's all quantum mechanical. If we look again at the molecule, I haven't counted them, but I think there are 16 DMF molecules. If you had done all this relaxed surface scan with everything at the PV0 level, it would have taken much longer for the scan. So maybe 10 times as long. So this is a good method to use for exploring chemical reactions in solution. So finally, I'm going to show where to get the XTB program from. So here, this is the address for the XTB program from the Grimmebrook Universität Bonn, but you can search this in Google. There's a link to the binaries, and there's a repository in GitHub and the online user guide. So this is the online user guide. It will tell you how to get the program. The precompiled binaries, you can get them from this latest release page in GitHub, which I'm going to show next. And it will tell you other ways of installing the program, how to set it up. So these are, for example, some of the variables that you need to declare. This number will change depending on how much memory you are putting per core, and also the number of threads here. And here is the latest release page, so it is here. So you can download this for Linux in several formats. This, I think, it only runs on Linux, which if you are serious about doing DFT or any kind of molecular calculations, you probably need to use Linux, or you're using a cluster that runs on Linux. So, and this is also the GitHub page where you can get all the source code, and you can look at it yourself, and you can maybe run it. You can run the program separately, of course. So I hope that this was useful for everybody. I know it's been a while since my last video, but I've been quite busy, so I'm hoping to get a few more videos more regularly now. Thank you very much. If you like this, please subscribe to the channel.